Hello, yeah, can you hear me? Hello. Okay, yeah, we'll get started in a couple of minutes. We'll wait for one or 2 minutes, and then we'll get started. Okay, yeah. So yeah, good evening. So yeah, welcome to the last problem-solving session for this course, optimization methods in civil engineering. So today we will see some problems. So actually, the whatever methods have been taught in class till now, we will solve some problems using Excel, using MATLAB, and also using R, so that you can use these softwares in future for your own project work. So we'll be solving some basic problems, and we'll solve see it, some basic concepts also. And if you have any doubts, like just feel free to ask me. Okay, yeah. So let's get started. So before proceeding to the problems, I will just brush up the concepts, because first we'll see some problems related to see how to solve a optimization problem using differential evolution, and then we will see how to solve a multi-objective problem using NSGA2 algorithm in R. After that, we'll proceed to solve problems in MATLAB, and then we'll see in Excel, because Excel is like for solving very basic problems. You can't solve complicated problems in Excel because it is not a very good platform for that. But yeah, you should know how to solve. Sometimes if you don't have access to the softwares, so you might want to use Excel for getting some quick solution for a simple problem. Okay, so yeah, let's get started. So this is differential evolution. I have discussed the concept regarding this differential evolution last class. So what are the steps involved? Steps are like, first you have to initialize the population. Then you will do the mutation. The mutation is slightly different here. Like we create a donor vector from the target vector, and then we do the recombination. Recombination is like we create a trial vector from a donor vector and target vector, and then we do the selection from the target vector, from a trial vector and a donor and a target vector. And after that, we set a termination criteria. Then we proceed to the next generation, and then we'll do these iterations till we get a optimal solution. So I won't go through all the steps, details of the steps again, because I have already discussed. The sir has also already discussed in the class. So we'll just see how to solve a problem in R using this differential evolution. Okay, yeah. Can you see my R screen now? I hope the screen is visible. Okay. So for solving a problem using differential evolution, first you have to install this package called DE-Optim in R. This is a package that has been developed for solving uh, differential evolution. So I'll just search. You can search the package here. If you search, yeah, this is the package, and these are the commands that are given in the function in order to solve a problem using differential evolution. So we'll solve two problems. One is the unconstrained optimization problem, and second is the constraint optimization problem. So how do we proceed? So in the thing is that for solving any problem in differential evolution, it should be minimization kind of problem, and uh, constants should be equal to greater than equal to type constants. So we should have a minimization type of problem. So yeah, so here is our function. So we define a function f1. So these first steps are for, I think, yeah, we'll just load this library. Yeah, we loaded this library DEOptim. Now first, before proceeding to solve, we will see how is the plot of the function. So it's just we have two variable function. It has the variables x1 and x2. It's like x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. We have seen this function before also. We have solved many problems using this function. So we will solve the same function here also. So we created the function f1. Now we initialize the values of x1 and x2. x1 and x2 start from 0 and they go up to 5, and we have an interval of 0.1, like all the values are like a interval of 0.1. So we created this x1 and x2 arrays. There are 51 values in both x1 and x2. Then we create a variable called z using the outer function, and this will find the value of the function at x1 and x2. So we have created the value of z. Now we use the parse function to see the 3D plot of the function or a surface plot. Yeah. So this is the surface plot corresponding to x1, x2, and z. And also we can see the contour plot. We can the contour plot, you can see, yeah, this is the contour plot. So you can see the minimum is somewhere here around 3.1 or 3.2, and in of x1, and for x2 it is around 1.8 or 2, somewhere in this range. So 2 and 3 somewhere, this will be somewhere near that. So we'll see the solution using this differential evolution. So in similar to GA and other methods that I have discussed in R, this function can also take only one variable. So we have to give the input to the variable in the form of a vector, that is x as a vector, so that the first element of x is the x1, the second element is the x2. So we have created a vector, so we'll define the function similarly. So function is like this, x1, we have function, created a function. Now we want to get the result using the this DE-Optim function. So yeah, here we have seen what are the commands in DE-Optim. First we have to give the function. So we have given the function here. Next is the lower bound. Lower bound we have seen it is 0, 0 for both x1 x2. So we give c 0, 0. Then the upper bound is 5 for both x1 and x2. So we give c 5, 5. And these are the only commands that we are giving now. So we won't be changing any other like the other parameters, that is the mutation probability and all these things we won't change now. So there are 200 iterations, and after 200 iterations we are getting this value, and the x1 value is 3, x2 value is 2, and the best fit the value is best value is the function value is 0. So we'll just give a summary of result. We'll plot this and we can see. The base member is 3 comma 2, like we have already seen in the plot. It is there 3 comma 2, and the value is 0, the function value is 0 at 3 comma 2, and after 200 generations and function evolution is 4200 times. Okay, you can also plot the result. You can see what we get. Yeah, I think if we maximize the, you can see, if we maximize the plot, you can see after around 25 or 10 20 iterations, the x1 value raises to 3 and it is constant henceforth. Similarly for x2, the value raises to 2, after that it is constant henceforth. Okay, so this is the problem how we solved using R. And yeah, so now this was like we didn't give any control, like we didn't set any like number, maximum number of iterations, or the this probability f, that is the what in mutation we have this parameter f in differential evolution, where we are taking the weighted average of the two vectors. So this weighted average factor, it can be given manually also. And there is a constant called C we have seen for recombination. Like when you're doing this recombination, we are setting a parameter, like if vn plus 1 is less than equal to C, that CR value is given as 0.7 here. We are setting it manually. Maximum iterations we are giving 100, and this population size is 40. Okay, so we are giving these controls now. The upper limit, lower limit are same. The function is same. So we'll see what is the result. We have got the same result even after this number of iterations. So we'll give the summary also. Yeah, around 100 iterations, base value is 0, 4400, 4040 times of function evaluations. Even now, I think you will get, yeah, the similar kind of functions. Okay, so this is very simple. You just give the commands accordingly based on the requirement of your function in constant optimization. So this is how you solve. So now we'll see one problem of constraint optimization. So in constant optimization, what we do? So we take this function. Like okay, first we will see the plots of the function. So how the plots look like. So we give a function. It function of x1 x2, x1 minus 2 whole square plus x2 minus 1 whole square. Now x1 and x2 goes from minus 5 to plus 5. We have given the range. Then we evaluate the function value for x1 x2, and now and then we see give a contour plot. See a contour plot. Yeah, I think, yeah, wait, I have to clear these plots. I'll clear all the plots and then yeah. So this is the contour plot. You can see at 2 comma, I think 2 comma 1.8 or something, you will have a minimum somewhere here. 2 comma 1.5 maybe, yeah. So we'll get now we have two constraints here. First constraint is uh, this one, that is x1 plus x2 minus 2. So we'll plot this function for this curve. Yeah, we got one curve, and this is the second curve. So yeah, so we have to satisfy these two constraints, that is less than equal to constraints. Sorry, greater than equal to constraints. So it's all the values should be in this part only. So and we should get the minimum value for this. Initially the minimum value was somewhere here without constraints. Now when you give the constant, the minimum value will be at this point. This is the intersection point, or at this point, but this is nearer to the, this point is nearer to the original minimum, so the function evolution will coming at this point. So we'll get the evolution using the this differential evolution. So how to create the function is like same like before. We give the function here inside the function, like we give the function definition, that objective function. Then we give the constraint 1, that is x1 plus x2 minus 2. Then we give the second constraint, that is x1 square minus x2, and we give the function value as like if we give a if else function, so if, so that when g1 less than equal to 0 and g2 less than equal to 0, we get f1, else we are getting a very small value. So we're giving the function like this, and yeah, we're defining the function. So we have defined the function. Now we'll see the result using d optim. So we give d optim, we give the lower bound, give the upper bound. We are not changing the other parameters. We'll just see these values. So we have got the results. So at best fit, we are getting the value at 1 comma 1. So this point will be at here 1, and also here it is at 1. Okay. So we'll plot this optimal point using what? Using result slash optims slash best member 1 and best member 2. So these are called yeah, this member 1 and first one is called a best member 1. The second one is second value is called a best member 2. This is a point type of point, and color is the we'll give a setting a color. So we'll see. Yeah, you can see a red dot here. So yeah, you can see a red dot here. This signifies that this value is the max like optimal value for this function, constant optimization function. Okay, so very simple to apply in R. You just like install the library, then load the library, give your function, and then just use the d optim function. That's all. So based on a requirement, you can use this function. In MATLAB, we have to write some more lines, some more functions sometimes. So, but it is easy in. Now we will see one problem using NSGA2. We have seen this NSGA2 algorithm before also. So just brush up of the NSGA2 algorithm. So NSGA2 is a non-dominated sorting genetic algorithm method. So it is used for solving multi-objective problems. So it is an elitist non-dominated sorting genetic algorithm to solve multi-objective optimization problem. It was developed by Professor Kaldan by Dev and a student at IIT Kanpur. It can converge to the global Pareto optimal front and can maintain the diversity of the population on the Pareto optimal front. So the diversity of population is well maintained in this method. So that is why it is a very good method for solving these multi-objective problems. So we have discussed what is non-dominated sorting. So what is the main concept here? It's like an individual x is said to dominate another individual y if and only if there is no objective of x worse than that of objective of y, and there is at least one objective of x better than that of objective of y. So these two things you have to keep in mind. It has been discussed very well in the class. And this method is based on a crowding distance, whereas NSGA, only NSGA is based on the sharing function. This is based on crowding distance. So how do we define the crowding distance? The crowding distance is the perimeter of the rectangle constituted by the two neighboring solutions. So if we have I minus 1 and if we are at solution I, so you have this point I minus 1 and I plus 1. We draw a rectangle so that these 2 points I minus 1 and I plus 1 fall in the diagonal of the rectangle. And diagonal of the rectangle. And now we'll see the perimeter of the rectangle. This perimeter of this rectangle is what gives the crowding distance. So if the crowding distance is more, then the solution is less crowded, and then if the crowding distance is less, means the solution is more crowded. So based on this method, so we define a crowded tournament operator. So a solution I wins a tournament with solution J if the solution I has a better rank than J, that is Ri is less than Rj. And if they have the same rank but I has a better crowding distance than J, then Ri is equal to Rj and Di is greater than Dj. Yeah. So one thing is like when we are doing this non-dominated sorting, we first give the rank. How we give the rank we have already seen before. That is in non-dominated way. We give the rank like we see the first four solutions in that line, and then we see the other solution that has been dominated by those solutions and give the rank like that. If two solutions have the same rank, in that case the crowding distance come into the picture, and if they have it come in the picture, and from based on a crowding distance we can say that solution I has a is a better solution than J if Ri is equal to Rj, but the crowding distance of I is greater than crowding distance of J. Di is greater than Dj. In that case, the solution I is a better solution than J. So these two factors you have to keep in mind. One is first always comes the rank. If the rank is less, it is the better solution, and if the ranks are equal, then the crowding distance should be greater for the solution I to be a better solution than J. So this is the method, and these are the steps involved in this NSDA2 algorithm. So we initialize the population of size n, then we calculate all the objective functions, then we rank the population according to non-dominating sorting criteria. So this criteria this has already been discussed in class already. So yeah, after giving the rank, we do the selection, crossover, mutation, similarly that we have done in GA. Similar method here, the selection, crossover, mutation. And after doing this, we calculate the objective function of the new population. We get a new population after crossover and mutation. We calculate the objective function, and now we combine the old population, new population. We combine this both, and we now again on we calculate the non-domination ranking of the combined population. After getting a non-dominated ranking, we also calculate the crowding distance of all the solutions. So based on this ranking and the crowding distance, we get the now we again sort the solutions based on these two criteria, and we get the n member from the combined population on the basis of rank and crowding distance. That is, we cannot change the population size, right? So we already have set the population size as n. So based on this rank from the old population, new population, we combine, we sort this based on the ranking and the crowding distance, and we get the top n solutions. And after that, we replace the parent solution population by the better members of the combined population, and then we proceed to the number of generations. Suppose we set termination criteria of around 100 generations. We do this, we repeat this for 100 generations, and we get the then Pareto optimal solution. Yeah, so this is the method. Uh, so now we'll see the code. In the code, you won't see the method in detail, obviously, because
অপশন দিল হ্যাঁ পিডিএফ কারণে
হ্যাঁ
এখন কেউ অপশন দিল পিডিএফ কারণে মক টেস্টে তারপর নিল না তখন
পিডিএফ কেউ না নিয়ে থাকবে না এখন যদি না দেয় তাহলে মেবি স্পেশাল স্ট্রিং
যদি পিডিএফ দিল অপশন তুই নিলি না তখন পাইও নিলি না তখন
ও তখন 10 লাখ টাকা বের করো ব্যাংকের থেকে জমা দিতে লাগবে আর নেক্সট 4 বছর নিচ থেকে ডিবার্ড
তুই গাইনি দিয়ে এরকম অবস্থা এখন তুই যদি পাই না নে পিডিএফ দিয়ে রেখে
yeah, sorry for that. Yeah, so now we will see the NSDA2 method using R. So you have to first install the packages. Install this package called NSDA2R using this function called install.packages. So yeah, I'll first clear the library and also we'll clear. So I have already installed the package, so I won't run this command again. So I will just load the library. So this is used for solving multi-objective problem. So the objective function should be minimization type, and the constraint should be greater than equal to type. So these are the two primary criteria for solving this multi-objective problem using NSDA2. First, we will see the unconstrained problem. Yeah. So in this objective function, there are two objective functions. One is the f1, that is f1 is equal to x. Now f2 is x2 square minus x1 minus of a into sine b by x1. So a and b values are given. So a is 0.2, b is 1. We have given the object. So when there are multiple objective functions, we will write those objective functions inside a function. So we write these functions inside here, and then we return r bind of, that is, we return the two functions, one below the another. That is, we are using the r bind function here. Okay. So we have defined the objective function. Now we just use the NSGA2 function. This is used for solving this problem using NSGA2. So what are the commands here? So I'll just see here. Yeah, the commands are this. So I have to give the function. Yeah, we are given the objective function. Then the second is the IDIM. IDIM is what? Input dimension. Input dimension is like what is the number of number of values that are given. That is x1 and x2. We have two functions, two values. So it will be 2. Also output will be 2. So the lower bounds are C 0, minus 2. We are giving based on the requirement, like based on the problem. Then upper bound is again C 1, 2. This is also based on the problem. Population size is 100 and the generations is 100. We are setting this manually and we will see the result. Oh yeah, sorry. I think I have to remove this comma. Yeah, so we have generated this function, generated the result. Then we will see the result and the plot. Yeah, so you can see this is the Pareto optimal front for this objective function. That is f1 and f2. You can see the values goes from 0 to 1. 0 to 1 for f1, and for f2 it goes from 0 to -1. So all the solutions are equally distributed along the Pareto optimal front. So you can pick any of this solution and it will be a best solution for the problem. So like this solution, suppose if you pick a solution here, this solution will be very good in terms of f1, but it won't be a very good solution in terms of f2. Similarly, if you pick a solution here, so it will be a very good solution in terms of f2, but it won't be a very good solution in terms of f1. But if we pick a solution in between, so this will have, we can teach like not minimum in either f1 and f2, but it is satisfying the Pareto optimal front. So this is also a very good solution. Okay, so this was the first problem using this unconstrained problem. So now we will see the constraint problem. So when we do a constraint problem, how do we do it? So like similarly here, we first set the objective function. The objective function is same. We have f1 equal to x1, f2 is equal to 1 plus x2 by x1, and we return the two functions is r bind. Okay, we set the objective function. Now we also give the constraints. So there are two constraints here. The constraints are also be given in the form of function. So g1 is x2 plus 9x1 minus 6, and g2 is x2 plus 9x1 minus 1. And we're returning the two functions again here. So this is the constraint function. Now we get the result. We give the objective function. These are the input dimension, output dimension. Lower bounds is C 0.1, 0. Upper bounds is C 1, 5. This will be given in problem. I am not setting it based just like that. So these values, upper bounds and lower bounds, are given in the problem only. And the constraints are given. This constraint command is used to give the constraints. That is const functory, and constraint dimension is also 2. That is there are two values, that is x1 and x2, based in the constant. So we run the command, we will see the plot. You can see after giving the constraints, the values are coming like this. You can see the Pareto optimal font has changed. The value of f2 goes from 0 to 40, and the value of f1 goes from around 0.1 to 0.8 around. Okay. So this is our NSGA2. You can solve this problem. You can also see the result here. Okay, let us see. What are the values? Yeah, for different values of yeah, you can see the value in the Pareto optimal front. So if you just click here, you can see what are the x1, x2 values in the Pareto optimal front. So there will be two values for each point. So you can see this is the x1, this is the x2. One is 0.85 and 1, so it will be around 0.85 and 1. This is point, and it goes all the way up to 400.67 and 1.11. You know, so there are some solutions where it is 35 and 0.1, 0.13, and it is around suppose 35 here. I think maximum is 40, yeah, 44. 44 is the maximum one, so it is at 44. The value is 0.11. This point here. Okay. So yeah, this is the solution using NSDA2. Okay, we'll see one or two problems. I think we have to solve. Okay, yeah, we'll solve these two questions. These are based on differential evolution only. So you have to solve using D in R. So yeah, we'll see the function. So we'll solve question number 9 first. So the function is x2 minus x1 minus 3 whole square plus x2 minus 3 whole square subject to 2x1 plus x2 less than equal to 2. So we'll solve this. So we'll directly write the function from in these terms. So we'll just copy this part and paste, and we will see give the function based on what is given. Okay, so what is our function? Our function is x1 minus 3 and x2 minus 3. So the x1 minus 3 and x2 minus 3. So the x1 minus 3 and x2 minus 3 whole square, and what is the constraint here? Constraint is 2x1 plus x2 less than equal to 2. So it is 2 star x1, 2x1 plus x2 minus 2, and there is no g2. If else g1 less than equals to 0 and f1, and this is the how we. So this is less than equal to 0 function, this is the f1, so we write the command in that way. Okay, so we have given the function f. Now we get the results. D optim f, and lower bound and upper bound is how much? Minus 5 to 5, and both minus 5 to 5. So minus 5 to minus c minus 5 plus 5 plus 5, yeah, everything is same. D optim. And so yeah, the best solution is 0 after 200 iterations. The base value is 9.8, and the parameter value was 0.2 and 1.6. So let us see. It is 9.8. The function value is 9.8. 9.8. Okay. So simple problem using differential evolution. I will see one more problem, same basic problem here. I think we'll see this problem. Just a second. I will just continue. Yeah. So this function is we use the starting point of 0, 0, and x1 and x2 goes from minus 6 to plus 6. So the function is again same, 10 f function is f of x1 x2, so this is the function. So we'll write the function now. We'll copy this thing. Okay, so it is unconstrained problem, so we'll just copy this. Okay. Okay, the function is 10 into x2 minus x1 square whole square. So it is like 10 star x2 minus x1 whole square x2 minus x1 whole square to the power whole square, and the second term is 1 minus x1 whole square. Yes. Okay, so this is the function. We have to we have to optimize using the optimum function, then lower bound and upper bound. The lower bound is minus 6, upper bound is plus 6, so it is minus 6, 6. So to get the value of 1 comma 1, yeah, the solution is 1 comma 1. Okay, so we give, even if we give a summary of results, so the base value is 0, the base member is 1 comma 1. Okay, simple problem, just to solve using R. Okay, so this was about. Any doubts till now in this, only in these steps? If you have any doubts, you can ask me, or else we'll proceed to MATLAB. Okay, fine, then if there are no doubts, we'll proceed to MATLAB now. We've discussed all these concepts. Okay, so in last class we have seen in MATLAB that how to solve the problems using this classical optimization. So today we will see how to solve using this meta heuristic method, that is genetic algorithm, multi-objective genetic algorithm, and particle swarm optimization. So we have set the working directory and everything, so we'll run. So we don't have any variables and any command lines now, so we are like won't be running this thing. So this is the function. So initially this is an unconstrained single variable optimization problem using particle swarm optimization. The function is 2x cubed minus 3x squared minus 12x plus 4. We have to optimize this, and the range is 0 to 8. So let us define the objective function. The objective function is defined as this: 2x cubed minus 3x squared minus 12x plus. Sorry. So we have run this command. So we have got this objective function, that is an objective function here. The lower bound is 0, upper bound is 8. So now we give these options. These options are not recursive, but if we want, we can give. think are there anything else? Okay, so let us see without options. We have given particle swarm, we have given the swarm size. Okay, so I think will it give? Okay, we have to give is I think as F options. So let's check. Okay, so particle swarm requires global optimization toolbox. So first we have to install this toolbox. Okay, let's see. I think home. Yeah, apps. Install app. Package. It's not here. I have this toolbox. Okay, 1 second. I have to install this package here. And it, yeah, yeah. This is the global optimization toolbox. Okay, I have to sign in. So yeah, this is installing now. So yeah, for GA and particle swarm, we have to install this global optimization toolbox. So just remember that when you are when you have to work with these functions. If you don't have this toolbox, you won't be able to run these functions. So it might take some time to install. Okay, optimization, global optimization, MATLAB, we have 394 MB. Yeah, let's skip install. Okay, so installation complete. We'll launch MATLAB now. Yeah, we have changed the working directory to week 12. Everything is fine. Okay, so the package is installed. Let us see if we can run the function now. So we define the objective function. The lower bound and upper bound is also defined. Then we give options. Okay, it is taking the options now, and we give options. So we run this command, and yeah, you can see the optimization ended. Relative change in the objective value over the last options, and maximum iterations less than options. So the value of x is 2, and the function value at x equal to 2 is minus 16. So yeah, so this is how you solve using the single variable optimization problem using particle swarm. So this was about a single variable. Now we will see a multivariable problem, and directly we will see the constraint problem only. In unconstraint, it is similar to here. Instead of x, there will be two functions, that is x1 and x2. So we have to give the function accordingly. So we'll see for these functions, this constraint multivariable function. So this is the function. As we minimize this function, it is x1 square plus x2 minus 11 whole square plus x2 square plus x1 minus 7 whole square. So these are the constant. One is x1 minus 5 whole square plus x2 to the power 13 is less than or equal to 26. 4x1 plus x2 less than or equal to 20. x1 x2 greater than or equal to 0, and 0 less than x1 x2 less than or equal to 5. So we'll clear the command window. We'll clear the command window. We'll clear the variables and close everything. So okay, we can set the values lower bound based on our requirement also. So we have given minus 50 50. So we can give zeros also, but yeah, we'll let us give so lower bound is 0. So we have given this 0 comma 0, and the upper bound is 5. So it is 5 into 1 comma 2. So these zeros and ones function we have discussed in last class. So we have given the fitness function is at that equal to O fun. So we will be defining the O fun function here. So what is the objective function? So it will have the one objective function, that is x1 square plus x2 minus 11. So we have to give x as a vector. So yeah, since we initialize the values as a vector, so it will be taking as a vector only, x1 and x1 x2 like this. So next is the constant. First constant is yeah, minus 26 plus x1 minus 5 whole square plus x2 whole square. Sorry, not x2 whole square, it is x2 to the power 13, right? x2 to the power 13. So this is less than or equal to 0 constant. Similarly, the second constant is minus 20 plus 4x1 plus we are taking 20 to the left hand side. Minus 20 plus 4x1 plus x2. Minus 20 plus 4 into x1 plus x2. And the condition you are getting is if c1 less than or equal to 0 and c2 less than or equal to 0, then function value is objective function. Else we are giving the objective function as a very high value, that is at 10 to the power 5. Since we are minimizing the function, we want the value the minimum. So if it is not satisfying this constraints, we are giving the function value as a very high value. Okay, so we run this function. Let us see, we'll run everything together. What is the so we have to define it in a new window. Okay, so let us do that only. It has told to give the function in a new file, so we will give it in a new file. Okay, so we have given the objective function as open. We have assigned a value to the fitness function, and now we will run the particle swarm optimization. So after running, we are getting these values. That is, the result is like x1 is 3.17 and x2 is 1.27, and the function value is 5.002. So you have seen, the thing is that in MATLAB we have to initialize the values like this. It is slightly convenient in R sometimes, so but yeah, it is similar here also. Okay, so any doubts in this particle swarm?
You break. Hello?
Yes. Yeah,
Good
you
evening,
have
sir.
you have any
Can
doubt?
you briefly tell what zeros and ones will do? Just
Yeah,
briefly, not too much. That zeros function and ones function.
yeah. Okay, zeros function is what we'll do.
Actually, I have missed the last class. That's
Okay. So when we're giving zeros 1, comma 2, it means the first element is the number of rows and the second element is the number of columns. So what we'll do, it will create a matrix of 1 row and 2 columns and fill the values with zeros. That is what zeros functions does. So like if you just run this function here, I will just show here. Okay, if you give suppose 2 comma 2, so it will create a matrix 2 by 2 matrix with values 0. So this is how the zeros functions is operating. Similarly, when you're giving ones, it will create a
okay, sir. Got
matrix of ones. Okay, you can press this, you can see it
yes,
is
sir.
giving. Yeah, this is what is the work of zeros and ones. Okay, so yeah, we will solve one or two problems. I think we have here. Yeah, so this is a optimization problem. So yeah, okay, find the optimum of the following function using particle swarm optimization method for a swarm size of 100 and generate a MATLAB code to solve this problem. So the same function that we have just seen. So the range is different and we have to give the swarm size as 100. So let us solve this. Uh, I think it is the third. Yeah. So these will borrow from here only. We will be borrow from here. Objective function is this one. X1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. Yeah, right. This is the function x plus. We are replacing y by x1, x and y by x1 and x2. I think that is not a problem because we want it as a matrix or as a array. Okay. So we give the lower bound and upper bound. Lower bound is -3 and upper bound is 3. So we give lower bound equals to -3 star once 1 comma. Okay. Since this is -3, so what will it do? It will create a, you can see it is creating a value array of -3 comma -3. Similarly, we give the upper bound 3 is the ones of 1 comma. So if we run this, we are getting the upper bound as 3 comma 3. We have the objective function. Okay, we have to give enter text, right? We are giving the function as a function. Now we'll give the these options and the particles from optimization. So the fitness function is what? It is OF. We have given the lower bound and upper bound. We have the options as particle swarm. Swarm size is how much? Swarm size is 100. So we give the swarm size here as 100. We run this part. We are given the options. Now we want x and the value of f. So use the particles from function. We give of. So here it will be 2 because we are using two-dimensional array. We have lower bound, we have upper bound, and we have given the options. So we run. So we are getting the value of x1 as 3, x2 as 2, and the function value is 10 to the power 1.7 10 to the minus 13. This is approximately equal to 0. So yeah, what is the solution? It is 3 comma 2. So answer is 3 comma 2. Okay. So similarly, we can solve this problem also. This is also a single particle swarm size is same, so the function is different. So we'll write the code for this function. So 100 plus 9x square minus 5 sine xy. Okay. Enter it. 100 plus 9x square plus 5. 9 x1 whole square minus of 5 sine of minus of 5 sine xy, the 5 sine x1 into x2 plus 9 y square plus y plus 9 square x2 whole square y square plus so we have to give a semicolon. It's like mandatory, is not mandatory. It's like we are not want to run everything in the command line. So that is why we given a semicolon. So it is 100 plus 9x square minus 5 sine xy plus 9y square plus xy. So y is replaced by x2 and x is given by x1. So this is the objective function. Yeah. So sorry, we are giving as f. So lower bound is equal to, I think it is going from -6 to 6. Yeah, -6. So we'll just copy this part. Instead of -3, we are giving -6 here. So we're generating the lower bound and upper bound, and now we'll just run this command. So its form size is 100, again same here, and it's the same function, two variables and options. So we run this, we get -0.01, -0.06, and the function value is 99.96. So -0.01, -0.06. So this is the answer. So we're getting the first option. Okay. So these two are the unconstant problems. Now we'll see one constant problem. So it is to minimize this function x1, x2 plus x2 plus 1, and these are the these are the constants. So we'll see this problem. So so it will be similarly. So we have to create the objective function. So yeah, let us create this function. Okay. We're creating a function, give some different name. Objective function x. So the function is what? x1, x2 plus x2 plus 1. So it is x1 x1 x2 plus x2 plus 1. x1 x2 plus x2 plus 1. So what is the first constant? First constant 15 plus x1 x2 minus 20 x1 minus 30 x2. So instead of minus 20, it is 15 plus 15 plus x1 x2 minus 20 x1 minus 30 x2. Okay, so this is the first constant. The second constant is what? Minus x1 x2 less minus 100. So 100 will be coming this side. So minus x1 x2 minus 100 minus 100 minus of x1. Okay, so this is the condition that if the first constant less than equal to 0, second constant less than equal to 0, then function is OF. Else we are getting the function as OF plus 10 to the power 5. So we save this as the objective function. The thing is that when you are saving a MATLAB function, you have to save the function is the same name that you are giving the function. You have given the function name as objective function obj fun. So we have to save this in the same name. Then only the code will take this function in that name. Okay. So we have saved this. So now we'll write the solve this problem. So yeah, this is the command. So the lower bound and upper bound we have to see. I think lower bound is 0 and upper bound is 5. So yeah, it is same here. Lower bound 0, upper bound 5. objective function n, and so we are giving the fitness function. We gave the lower bound, upper bound, so we'll run that. So the x1 value is 5, x2 is 0, and the function value is 1. So the function value is 1. So this is the second option is the answer. Okay. So this is our particle swarm optimization. So you have to, for if we have a function with constraints, you have to create a function separately. You can. It's always good to create the function in a separate file so that it is, and it will save it in the same directory that you are working. Your function should be saved in the same directory, then only it will take the function. If you save the function in some different directory, then it won't be taking the function. Just remember that. And the second important thing is you have to save the function in the same name that you have given the function. So these two commands you have to remember, and else you just have to use the global optimization toolbox, and you can use the particle swarm function when you are working in MATLAB. Okay. So this was about particle swarm. So we'll see one or two problems using genetic algorithm. I think here also, yeah, we'll see. We'll clear everything. So we'll solve that whatever similar problem that we have seen, that same function using GA. We should give the same answer. The lower bound is -3, -3. You can give the bounds here as this or this way also, or you can give the bounds as this using zeros and ones function also. So I'm giving it like this. So it is. So in before going to GA. So before going to GA, some important things. Yeah. So when you are using this GA function in R, so it will have these commands. One is the function that we are giving x0, initial value. A is the matrix for this. Suppose these are the constants that are able to that is the function is subjected to, and here ax is the linear constraint, and a is the matrix of the coefficients of the linear equations. So a matrix is the coefficient linear equations, and so linear inequality constants. A equivalent, a eq is the matrix of the coefficients of the equality constants of the linear equality constants. beq is the function for, like, it's not a matrix, is the simple line function, that is b and b are vectors. Again, I think b is here. Yeah, b is also for like less than equal to constraint, but is a vector, not a matrix. B equivalent is for the equality constraint, for linear equality constraint, but it is a vector, not a matrix. Lower bound and upper bound are the same. Then non-linear condition. So you can set a non-linear conditions based on this. That is cx less than equal to 0 and c equivalent x equal to 0. So one is less than equal to constant and one is equal to constants, and C and C equivalent are the functions that return vectors. And the other thing is the options. Options you can set, like what is the, you can give your own function for their constants, or you can also give the selection function. There is number of parents. You can give number, like crossover probability, the mutation probability. So these functions, these options you can change in the options pattern in GA. So you can go through the documentation of GA. Everything is given in detail. So you can see through that. These are just basics I am giving you. So when there are no values given for like some constant, you can just put a blank matrix and you can run the GA command. So we are running this. So here this lower bound is given, the upper bound is given. Then a value is not there because we don't. It is unconstant problem. So there won't be any constants. So a is blank, b is blank, a equivalent is blank, b equivalent is blank. No non-linear constant, so blank. Interior condition also blank. And so we run this command, that is genetic algorithm objective function, that is two variables a b, and we give it for this. So we run this and we get the values of x as -2.8 and 3, and the function value is 0.66. Okay. So this is the unconstrained problem. So you have to give all the commands here. It is slightly simpler in R because you need not give this matrix differently. In R, you can just give everything in one function and just run the function. So R is sometimes more convenient to use compared to MATLAB. So now we'll solve a constraint problem. So in constraint, we'll have this objective function is same, but we have this constant, that is, we have seen the same constant, that is x1 minus 5 whole square plus x2 to the power 13 minus 26 and 4x1 plus x2 minus 20. So we have given the objective function. We have given the objective function. It is same. Okay. Lower bound is 0. Upper bound is 5. 0, 0, 5, 5. A, B. The linear constraints are 0, so like no linear constraints, so we keep as blank. So now there is a non-linear constraint. A non-linear constraint is given as, it is a function of x, that is c equivalent is 0, but there are two inequality constraints, that is c1, which is x1 minus 5 whole square, this is less than equal to 0, and the second is the c2, this is also less than equal to 0. So, and this is the GA objective function. We give the objective function, then we give the two variables a, b, everything is given, non-linear condition is given, integration condition is given. So we'll just run this and see if it runs. Okay, so it is not running, so again we have to give this function as a separate code. Okay, so yeah, we'll save it as nlcon. Save this as nlcon. Okay, now we'll just run this. Yeah, we are getting these values after constraints, getting 3.17 and 1.27, and the function value is 5.022. Okay, so this was our GA. I think you can solve one more problem. This is particle swarm, this is differential evolution. Yeah, we'll solve this problem. This is the same function only. Oh, I think function value is 5. Yeah, we have solved this problem. 5.022. Yeah, this is the same function that we have solved. So yeah, so this is about. Is there one more problem? Yeah, we can solve this problem also. This is again one equality constant is there, so we'll just solve this problem. Okay. So function is 3x1 square plus minus 2x2. Problem. So yeah, we'll give this, copy this. So so what is the function? The function is 3x1 square minus 2x2. 3 is x1 whole square minus 2x2, right? Variable lower bound is 0 into 1s. So our range is minus 5 to 5, so it will be lower bound is minus 5 into and upper bound is 5. We have generated lower bound and upper bound. We have set the objective. Now we have to set the constraints. So yeah, C equivalent is not 0, it won't be blank here because we have a equality constant. So equality constant is 2x1 plus x2. 2x1 plus x2 minus 4. 2 star x1 plus x2 minus 4. And there is no C2, so there will be only one inequality constant. And so C is what? X1 square plus x2 square minus 19.4. X1 square plus x2 square minus 19. Okay, so we'll save this function in the same name. Yeah, now we have to give the direct on assignment. So this A, B, everything is here 0. Again, I'm borrowing from there only. Lower bound is upper bound I have changed. So it's integer con. So we'll see. So we are getting the function values minus 8.6 and the the x and y values are minus 0.2 and 4.4. So let us see. So the function value is minus 8.68. We are getting it minus 8.68. Okay. So this is the answer. So similarly, you can solve like single variable problems also and unconstrained problems also. And I'll just go through this multi-objective problem. So multi-objective problem is always easier to solve in R, but still we'll see what. So in here for NSGA you have to create your own function. There is no predefined function, but for like MOGA algorithm, there is multi-objective GA. For that there is a function, so and we'll be using that only. This has been discussed in class already, but I will still go through it. So lower bound and upper bound is given. The objective function is @ function. Nonlinear function is this one. A, B, these are equal to these are blank. So we are giving the options. Options are one given a maximum generation as 600, population size as 1000. The mutation you are giving as Gaussian mutation. You can give normal mutation also. And you are GA plot. You are plotting the Pareto optimal front. So this is called GA plot Pareto. So we are running these options. So yeah, can we run everything? Again, I think you'll have to create this function. Yeah, so this is the disadvantage of MATLAB. You have to create a function every time in a separate. So we created a function. One is the objective function. There are two objective functions. F1 is x, F2 is 1 plus x2 into exponent of minus x1 by 1 plus x2. And the objective function is the matrix of F1 and F2. We're creating this. Then there is this function of constraints. I think this also we will have to create in separate. Function of constraints. C equivalent is blank. F1 is x, x1. F2 is 1 plus x2 into e to the power minus x1 plus 1 plus x2. Okay, yeah. Okay, so this problem is like without using the constraints, and this is using the constraints. Okay. So we have defined C1 and C2 as the constraints here, I think. So we have set this function. Now we can run the objective function. Easier to set the two objective functions also. We'll run this, and yeah, we're getting this plot. You can see this is the Pareto optimal font that you are getting for this multi-objective GA problem. So it is slightly taking a bit more time than compared to R. R is like more like faster than this one, faster than MATLAB. So this code is already been solved by sir. You can just go through that lecture again if you want. So it is simple. Okay. So this was our multi-objective GA and also GA and everything how we solve in R in MATLAB. Sorry. So now I'll just go through the basics in Excel. You can solve any problem in Excel also. So we'll just see how to solve one problem in Excel. Okay. So yeah, we can solve. So this is the same problem that was solved in class. So I think you can give 0, give 0. So here this is a problem that is already been solved in class. So initially the x1 and x2 are given as 0. These values, then we create an objective function. So it is d2, that is x1 minus 2 whole square plus x3 plus x2 minus 1 whole square. This is the objective function. We are giving it as like this. This is in Excel. Now the constant one function first is x1 plus x2 minus 2 is less than or equal to 0, and the second is x1 square minus of x2 is less than or equal to 0. So this is the thing. Then we go how to solve. We go to solver. We have to find the minimization. So we set this objective. In the objective, we give the location of this value. That is the objective function value that we have to minimize. Then by changing the variable cells, that is this variable cells we have changed, that is d2 and d3, d2 and d3. And then subject to the constraints, you can add the constraints using the add function. Okay, I will just add it again. So we'll add the constraints again. So what is cell reference? Cell reference is the left hand side, less than equal to constraint, and our constraint value is how much? 0. So we give this and okay. This is so first is created. Again we can create the second constraint. We give the cell reference the first one, then the constraint value is 0, and okay. We get the two functions. You can use GRG nonlinear, or you can use simplex, or you can use evolutionary. So if we give GRG nonlinear, you can solve. You can see the answer. So we give the answer of, you can see the function value is 1 and function value is 1 and x1 and x2 are 1. So this is the x1 and x2. Original value is 0, final value is 0.99, it is 1. x2 is 1 and also g1 and g2 are satisfied. The function value is 1. You can see this is the final. You can see the results like this. I think there is one more problem here. This is unconstrained problem, that is consider a function x4 plus 8x square minus 3 using Excel to find the value of x and minimize the function f. If the selected method is Excel GRG non-zero, which of the following is correct. Okay, so with a simple problem only, we get variable. We give some value of x. Let us give it as 0. Objective function. It is f1, which is equal to how much? x4 plus 8x square minus 3. So it's equal to x to the power 4 plus 8x square, right? Yeah. Plus 8 star x square minus 3. Okay, we have given this function, so there are no constraints here. We'll just use the Excel solver. So we'll remove for here. We'll select the objective function as this one. Okay, we'll delete the constraints by changing the variable cells. Which one? This one. We are using GRG non-linear only. D11 we are changing and D13 value we have to find. So we go to solve. We'll see the answer. So we see the answer report. The final value is minus 3 and x is 0, I think. Yeah, it's okay. So the thing is that we already have given 0. So let us give some different initial value and then check. We give x as something 2. Okay. We gave x as 2 and now we will do the solve. It is we have to change this using GRG non-linear and then solve. Okay. So now you can see after solving you are getting the x value is 0 and the function as minus 3. Okay. So it is like for simple problems you can use Excel also. It is, but for complicated problems you cannot use Excel, like for using GA and particle swarm and these methods. So yeah, that was all for today. Like if you have any doubts you can ask me now, or else I will end this session.
Sir,
Yeah.
for an exam point of view, that is the final exam we are having on 28th.
Yeah.
Yeah, for that coding is not possible to do there. No, what type of can we expect around last 4 weeks? It will be on the same assignment pattern.
Yeah, it will be in the assignment pattern mostly, and yeah, it will be, he will be asking, like, actually I won't be setting the paper will be set by the faculty only. So the thing is that yeah, it will be mostly in the assignment pattern, but
Yeah.
so he will be asking questions like we have learned the initial methods, right? Simplex and these methods, and even for genetic algorithm and all. Like he has shown like some
Yeah.
problems, right? The initial, like how to do the mutation, how to do the crossover using like very simple 1 or 2 values, right? Like that, right? So he will be asking mostly the basics of these things. Coding, I don't think he will be asking. Mostly, I don't think
Okay.
he will be asking too much of coding, because I don't think if the exam is offline, it's offline, right?
Okay.
Or exam is like you have to write, or
Yeah,
just
it's offline. It's protocol exam.
yeah, then I don't think he
No,
will be
no,
giving.
no. The multiple choice.
Okay, then I don't, he might be
Okay.
giving coding, but I don't think he will be giving too much of coding. Like in assignment there are some problems now, like if you give what kind of error code will be coming, or what type of command is this, so these small things he might be giving, but like to
Yeah.
solve a problem by code, like I don't think
Okay.
it will be coming. Yeah. So yeah, and focus on the concepts, like
Yeah.
like
Okay.
how to do the
That
mutation. Yeah. Yeah, you were
The
saying something?
genetic algorithm and remaining particle swarm also,
The thing is that for solving any
we
problem,
cannot do that.
yeah, you cannot do it by hand. Only genetic algorithm, basic, like, well, in a initial class, in the basics, he taught something, right? Like using like only small vectors, how to change the
Yes.
bit size and everything, like change the due to mutation. So these small things he can ask, okay, in genetic algorithm.
Yeah.
But for particle swarm and NSGA and these
Okay.
complicated algorithms, like he will be asking the concepts only, like what is the recombination, how it is done, these small things in NSGA.
Okay.
So these small conceptual things only, not the codes, because the
Okay.
coding is complicated.
Yeah. Yeah. Okay. Okay.
Yeah, that's, I think
Thank
that
you,
will
sir.
be, yeah, okay. Welcome. Anything else? If there's nothing else, we can end today's session, I think. Yeah.
Yeah, sir. Thank you very much for your cooperation around throughout the lectures. We got to solve some assignments also. Thank you.
Okay, welcome. Yeah, anytime you have any other doubts, like you can ask me sometime. I think you have my mail ID, right? In that, I think in the course, I think the mail ID is given
Once
maybe.
you drop in
Yeah, you can sometimes, if you have anything, you can drop a email. I'll reply to it. Okay.
yeah, can you once drop it in chat box, your mail ID?
Okay, yeah. I think it's. Yeah, so yeah, I have given my mail ID in chat box. You can just note it down. Yeah, if you have anything, any queries, you can ask me before the exam.
Sir,
Yeah,
assignment
okay.
5
Thank
to 11 solutions are not released till now, sir.
I think it will be released in 1 or 2 days, maybe. I think NPTL, it's like it's not in my hand. The NPTL authority only releases. So I think they will be releasing together with SR 12, I think.
Okay, that assignment 7 and 8 revised.
I don't know. Like, I have given the option, like opinion to sir, like that there are some mistakes. He told that he will contact NPTL, because I cannot contact NPTL directly to change. It has to come through the faculty. So after that, I don't know, like whether he has given it, like whether NPTL is taking action on that or not. I told sir. So I think they might be taking something, or else like not to worry much. Anyways, like it's just
Okay.
okay. Okay then. Thank you for attending all the sessions, and also all the best for your exams. Okay. Have a good evening. Bye bye.
you, sir. Thank you very much.
Yeah. Welcome. Bye.
Bye.